Hey everybody, welcome back. This is part 2 of our deep dive into where do plants come from. In our last episode, we traced life from its beginning, or what we think is the beginning, again, not your preacher, all the way to the moment that a eukaryotic cell, an archaic eukaryotic cell, engulfed the photosynthetic cyanobacterium, creating the chloroplast, which was the defining apomorphy or enhanced trait that a progeny displays. This is the primary apomorphy that gave rise to what we're going to talk about today, which is algae. Everybody knows what algae is. But before we get into that, before we get into algae and all of that, I wanted to go over something that is important that's going to help us navigate this phylogenetic tree of life, which is how to read a phylogenetic tree. It's super basic and this won't take long. I just wanted to explain this so that we can track this together, so to speak. Anyways, but essentially we have been talking this whole time about the genre Archaeplastidia, which are the eukaryotic cells that would have engulfed the cyanobacteria, the photosynthetic cyanobacteria, giving rise to not only green algae, but where you see the Archaeplastidia split into green algae, red algae, and Glaucophyta, which I believe is brown algae. They're all photosynthetic, and that apomorphy gave rise to these 3 different branches that utilize that apomorphy in different ways. So these relationships are not guesses. They're built from molecular phylogenetics, comparing DNA and protein sequences across organisms. In the late 20th century, scientists like Carl Woese revolutionized biology by sequencing RNA genes, which act as these molecular timekeepers and molecular logs of DNA, where we can see almost from the beginning what genes were activated, what genes were turned off, and kind of like a mark of ancestry, we can compare these hereditary factors to other DNA to show likeness. So after the chloroplast origin, our lineage, the Archaeplastidia, branched into 3 major groups: Glaucophyta, which are rare today, with primitive chloroplasts that still surround a thin wall left over from their cyanobacteria ancestor; the Rhodophyta, which are red algae, which evolved unique pigments like phytoceracin, which allowed them to photosynthesize in deeper waters and in places with less light. The branch that we're going to be focused on, Chlorophyta, which is the green algae, are the direct ancestors of land plants, with chlorophyll type B along with chlorophyll type A, giving them greater efficiency in capturing light, which is kind of foreboding and foreshadowing a even more revolutionized apomorphy on that photosynthetic property that it already is displaying. This classification was confirmed in the 1980s and 90s when molecular phylogeneticists, led by researchers like Douglas and Turner in 1981, and I'm going to butcher this name, but Bhattacharya in 1995, they compared chloroplast DNA sequences and revealed these deep splits, which helped confirm these places within the phylogenetic tree with this molecular data they were able to find. Anyways, getting into Chlorophyta, finally, green algae, something that can finally photosynthesize an organism, which its derivation of ATP is primarily focused on photosynthesizing. In coastal waters all around very, very primitive Earth, this would have been around during like Gondwana, so way before Pangea, right when Earth was prime and forming and getting warm waters with big coastal bodies. So in these coastal waters, Chlorophyta would have diversified, and many stayed very microscopic, very small, but some began forming these dense colonies, something like volvox, but while others developed more complex bodies, fossils that were found, like that of Proto-Rocledius antiquus, I think that's how you pronounce that. Sorry, my Latin is terrible. Anyways, that fossil was discovered in 2020 in a billion-year-old carbon-dated Chinese rock. by a Kin Tang and his colleagues, and it proves that large green seaweeds existed long before plants took root on land. So among this green algae, we diverge into...
What are you doing?
I'm trying to give a lecture. Will you go play?
Why are you doing a lecture?
Because I'm trying to teach people about plants.
What's the name?
That it's a bunch of people. Why don't you go play your toys? Among the green algae, a special branch, the Caryophyta, began evolving traits that would one day allow life to leave water. Some of those particular apomorphies are Ugumi, which sounds insane, but basically it's producing large non-motile eggs and smaller sperm. So this is the beginnings of the plant versions of sperm in the egg. That's just a precursor to something that is needed for plants to eventually make the jump to land. So just remember that, sperm in the egg. This delineation, the Charophyta, which come right after the Chlorophyta, have a little, I don't know how well you can read that. Here we are with the Archaeplastidia, then it branches, and then the branch that we're following that takes us to land plants is here. We're talking about the Charophytas right there. I don't know how well you can see that. I'll pull another one up on screen. Anyways, some other notable apomorphies that they made are the protective coatings around the spore walls, which shielded against drying and UV light, which allowed for land colonization, and was a precursor that eventually developed to add to land colonization. And they also had parenchymus growth, which is sheet or tissues of cells that could develop into more complex forms. This was the beginning of differentiation, which is plants' ability to be able to change apical cells, parenchymal cells, any kind of cells into any other kind of cell that they need. This is kind of one of the reasons that we're able to clone plants, but we'll talk more about that later. So fossilized resistant spores from the Middle Ordovician about 470 million years ago, found by Strother and colleagues in 1996, provide the earliest evidence for plants preparing for land with these apomorphies, the Charophyta. But in the next episode, we get to finally talk about the beginning steps of land plants. So we'll witness one of the most daring moves in evolutionary history, at least for plants, is when green plants left the safety of the oceans and stepped onto barren land, which doesn't sound like a lot, but when you think about it and you conceptualize the morphological changes that plants have to make to get from just Charophyta into the Embryophyta, which are the beginning steps of land plants. In water, there is no weight. Think about how heavy whales actually are. But when they're in water, there is no weight because water alleviates so much density, because water is so much denser than everything else. That applies to plants, algae, and anything, and seaweeds as well. So think about when the tide sucks out. All of the plants in the water, they lay down because they don't have vascular tissue or morphological capabilities to be able to cope with that. So it's a significant step in evolution for these plants, the Charophyta, to be able to create an apomorphy in which they are actually able to be on land. But more about that in the next episode. Thank you so much for watching. This has been a lot of fun to make, and I appreciate all the feedback both here on TikTok and also here on YouTube, because I've been uploading it in multiple places. Anyways, thanks so much for watching. I appreciate all the love and support so far. One more disclaimer I did want to add is that this is a vast and broad evolutionary chain, and there's going to be things that I miss. There's going to be apomorphies I don't mention. There's going to be details that I leave out, but I'm going to do my best to hone in on every single genre of this phylogenetic tree so that we can understand the roadmap of just where plants came from, why that matters, and why they're important especially. Thanks so much for watching. I'll catch you next time.